Next, we are going to hear from Dr. Jenny Sideri, working with Thornton Tomasetti in New York. She is working with the forensics team. So Jenny, the floor is yours.
Thank you so much, Toma, for the introduction. My name is Jenny Sideri, and I'm an associate at Thornton Tomasetti, and I work at their New York office. So this presentation is about a case study project that we have applied performance-based structural fire design at a high-rise building. This project included analysis in SAFIR, of course, but also other software. So I will focus today on kind of both, and also mainly on the big picture goals and results of the project, while diving a little bit into the details of the analysis. So a little bit about the motivation for this project. We all know that prescriptive design has overall increased, of course, fire safety, but is not the safest or the best design, especially because safety is only presumed and not quantified. So on the other hand, performance-based structural fire design, or PBSFD, is a customized and rational design that studies what are the acceptable consequences of a real building response under real fire hazards. So let's talk about the US now. So previous guidance in the US regarding structural fire engineering includes documents published by the American Society of Civil Engineers, or ASCE, and also we have material-specific codes, including steel, concrete, and timber, all having new chapters related to fire recently. So PBSFD is particularly significant now in our application for tall buildings because occupant evacuation can be very long. There are many challenges to firefighting. Tall buildings can have very complex structural systems, and that means the consequences of failure can be very detrimental, especially in an urban, dense environment like New York, for example. So an overview of what the project is. So there were two previous publications by ASCE related to structural fire engineering. Now, this one is the one that came out in 2020, which is a third one that expands basically on the theoretical background provided before with a practical application. So this publication presents example designs of proper application of PBSFD. It's very important for the engineering community in the States because it's first of a kind. It included 4 structural engineering firms that were selected as the design teams to develop 4 exemplar building designs, and Thornton Tomasetti was one of them. And all 4 designs were peer-reviewed in a collaborative way with expert academicians, including Professor Negar Elham Khorasani, Professor Erika Fisser, Professor Thomas Guernay, and Professor Jose Torero. And it was actually a very fun experience, and I feel very glad that I was included in that, especially collaborating with you, Thomas, and Negar, and the rest of the professors. That was a really rewarding experience. So now let's talk about the building. We have a high-rise 50-story building, which is mixed use, residential and office. It is located at the Midwest of US, and it has a risk category 3. The lower 30 floors are office floors with steel beams and columns and wide column spacing. The primary steel members have a 3-hour fire rating per code requirements, and the secondary members have a 2-hour rating. And this can be achieved with fireproofing and insulation, in this case with spray fireproofing, SFRM. Now, the 20 upper floors are residential with concrete columns and slabs, and because they're residential, they have denser column spacing. Now, we have a mismatch in the column locations, and in order to achieve the transfer of loads between those, we have a transfer level at the 30th floor with several steel trusses that are interconnected. And finally, to resist lateral loads, the building has 2 concrete cores. And then for PBSFD, we consider 2 features of the building. First, the typical bay of the steel frame of the 30 lower office floors. And then we consider the transfer trusses as a unique structural feature of the building. This is our design strategy. We have design 0, 1, 2, 3. So design 0 essentially is the prescriptive design. There is no engineering involved, and then that means our performance is indeterminate. Now, design 1, 2, or 3 are performance-based. Design 1, we can apply fireproofing as needed to satisfy safe evacuation of all occupants to a refuge area. And this design is actually not applicable to us for a high-rise building because evacuation might take several hours and it will last longer than the fire rating. So that brings us to design 2, which is again a performance-based approach, where we apply fireproofing as needed so that we don't have any collapse of the structure until full fire burnout. Now, this is an engineered approach, but we can only modify the insulation. We cannot modify the structural system. And as we will see later in the presentation, we could not achieve design 2 for the typical bay because we could not accommodate the connection demands by only adjusting fireproofing. So now that brings us to the design 3, which is again performance-based, and we can modify both the fireproofing and the structural system to achieve full fire burnout without any collapse. And this is a design that we achieved the desired performance, and we actually had additional benefits, including cost savings and better environmental impact. Now let's describe our fire scenarios. Choosing, of course, our fire scenarios is very important as they significantly affect the structural response to fire. And we should consider several factors, such as the AHJ requirements, likelihood and intensity of the fire, and space compartmentation. First, we have fire scenario 1, which is a localized fire of an office workstation that ignites next to a perimeter column with an HRR time history taken by NIST experiments. To simulate this scenario, we created an FDS model and measured the temperature time histories at various points on beams and columns, as you see here in the graph. So following the localized scenario, now we have 2 scenarios that are compartment fires. One for typical bay and one for transfer trusses. We use the Eurocode methodology with varying factors that affect the fire dynamics, such as ventilation, geometry of the compartment, fuel load, and sprinkler activation. The resulting fires are shown in this picture. They all represent realistic fires that the AHJ, the structural fire engineer, and all the project stakeholders, they can choose from. And they range from moderate to more severe exposures. For example, let's take the compartment fire under the transfer trusses. We have the scenarios in the red lines, which is a time history of the temperature. The red dashed line is the moderate scenario, and the red solid line is the more severe scenario. Now let's go over our thermal and structural analysis and the design iterations for the typical bay. We built a 3D finite element model of a typical beam slab column subassembly in Abacus. That is not a SAFIR analysis, so that's why I will quickly go over it, but it's a main part of our project. So we basically modeled the wide flange steel beams with equivalent concrete slab strips to consider their composite action. And we modeled the steel column and also the steel shear tab plates representing the connections. And we considered temperature-dependent thermal and mechanical properties explicitly per the Eurocodes, as well as we considered geometric nonlinearities in order to capture any buckling failure modes. We also consider the behavior of connections by adding several contact features between the members. And now as for the design iterations, we performed analysis for 1 hour, 2 hour, and 3 hour protected steel for the 3 scenarios, fire scenarios. And for each analysis, we extracted time histories of the beam's vertical displacement, temperatures at various locations, connection forces, as well as concrete slab forces, and we checked them all against capacities at elevated temperatures. As an example, in the lower right figure, you can see a contact between column and bottom beam flange that occurred in one of the scenarios. You can also see the local beam, web, and flange buckling that occurred at one of the design iterations. Quickly, I'll go through the design summary. These are the results for the typical bay. First, we found that the beams had adequate capacity to withstand the fire with net reduction in fireproofing, depending on the fire scenario. So that was good that we were able to reduce the fireproofing, meaning also the cost of the project. Now, for connections, we concluded that with design 2, meaning by only adjusting the fireproofing, it was not sufficient to reduce forces within the connection capacity. But with design 3, remember, we are able to modify both the fireproofing and the structure. We are able to properly design the connections to withstand the fire exposure. What we did was we locally increased the fireproofing at the connections, and we also introduced horizontal slots to relieve the large axial forces during heating and cooling. So we modified essentially the connection so that they are slip critical, and they're designed to not slip at ambient conditions, but they only slip during fire. And at all times, they're able to sustain gravity loads and also the column bracing loads that are essential in a high-rise building. Now, for the columns, we found that they had adequate capacity, reserve capacity to survive the fire under axial loads with lower amount of fireproofing. So again, reduction in fireproofing here. We also found the additional bending demand and deformation due to the beam's thermal expansion was acceptable. Okay. So now we're going to talk about the transfer trusses that is actually done in SAFIR. So this is our finite element model. I will quickly touch base on the modeling side, but my main focus will be on the results and the conclusions. So we built that 3D model, as you see here, of only the upper 30 stories of the building, which were the residential concrete, as well as the steel transfer trusses of the 30th level. You can see here the 3D view of the model, the plan view showing the concrete cores and the two side views. And the shaded red box over here is the fire room, which is a mechanical space under the transfer trusses. So the transfer trusses were modeled as protected wide flange steel sections with steel material degradation explicitly included in SAFIR. And the two-way concrete flat slabs were now modeled as equivalent slab strips per ACI. So both the steel beams and the strips, concrete strips, were modeled as beam elements in SAFIR. And here on the left, you can see a typical I-beam section of the trusses. The graph shows an example of a heat transfer analysis on this member with different fire ratings. We plotted the time history of the temperatures of the outer fireproofing, and then within the steel for 1 hour, 2 hours, and 3 hour rating. And then also you have, we had at the transfer level, we had a slab system. So here you can see the concrete T-beam at the transfer level, another heat transfer analysis as an example. So this was applied at the transfer level at the upper chord of the truss. So now let's talk about the design iterations and the summary. So we analyzed different options with different fireproofing ratings ranging from 1 hour to 3 hour for both the severe and the moderate fire scenarios. So we did heat transfer and subsequent structural analysis, and the results showed that certain truss members buckled during the analysis, but in most cases, the loads could redistribute in the model, and then the analysis was able to continue running without the structure collapsing. And for the trusses, I wanted to note that we only consider design 2, that includes fireproofing modifications. We didn't consider design 3 because we said it's similar to design 2 in the sense that structural modifications of the trusses in order to create alternative load paths would not provide a more efficient way to achieve the performance goals. So essentially providing additional fireproofing locally was a limited cost solution, and it's a more straightforward solution. So we only had design 2 for performance-based. So now design 2 was achieved with severe fire rating, with several fire rating ratings and fire scenario combinations that met the performance criteria, but they corresponded to different truss deflections and different extent of impact on the upper floors, because the trusses support all the upper floors of the building, so they have significant impact. Let's take an example. For fire scenario 3B, which is the more severe scenario, if we have a 3-hour rating on all trusses, this is design 0, meaning prescriptive. I'm sorry, I meant 3A scenario. So design 0 is prescriptive. If we reduce to 1-hour rating for all the trusses, then we see collapse. So that is an unacceptable design, of course. So now if we reduce the fireproofing rating to 2 hours for all trusses, we have 2 members of the perimeter trusses buckling, but with load redistribution, collapse is prevented. We have a deflection of about L/397 approximately, and a maximum DCR of the slabs above equal to 90%. And this is all acceptable design. Now, let's say we have a 2-hour rating on interior trusses, but a 3-hour rating on perimeter trusses. So in that case, we have only 1 member buckling, and we have a little less deflection, L/4 for 1. So with all this, I'm trying to say that, you know, the design team or the building owner or the ASJ can choose the amount of deflection that they deem acceptable for a design. And they can choose the corresponding amount of fireproofing for this deflection, like anything from this table. We remember that, you know, deflection has a very large impact because it will affect all the residential stories above the trusses and also any repairs that may be needed after a fire. Another thing to consider is that the ASJ or the owner may want to limit any buckling of truss members, even if load redistribution after buckling prevents collapse of the structure. They may consider that buckling of any primary gravity member is a near collapse, and that is not an acceptable level of performance. So again, fireproofing may be adjusted to match what is the desired performance in terms of deflection, buckling, and so on. This is another table that summarizes the different designs for the transfer trusses in a more qualitative way. For example, again, if we choose to design for the severe fire scenario, if we have a 1-hour rating on the inner trusses and a 3-hour rating on the perimeter trusses, then we see that the allowable damage is cosmetic only on the floors above, and we have some limited buckling in some trusses. So to conclude, let's summarize this exemplar high-rise building design. We first of all identified deficiencies of the prescriptive code because the code-compliant design did not perform adequately for structural safety as related to the connections, especially in this study. And the best design that we achieved is when we can do modifications both to the structural design and the fireproofing. And we can have many different types of solutions available to achieve a safe design. We can do changes to the structural members, to the detailing, to the connections. We can redistribute fireproofing. We can change the geometry and compartmentation of the space. But in the end, PB-SFT can improve safety, but not only safety, but also cost, aesthetics, schedule of construction, carbon footprint, and can provide us with additional design flexibility. So thank you very much. With that, I welcome any questions.
Thank you so much, Jenny.
Thank you, Thomas, for this opportunity working together. It was fun.
It certainly was, and we learned a great deal all together working collaboratively. So thank you a lot for this presentation. Can you explain in the genesis or the development of the project what design 0, 1, 2, and 3, what they meant to represent for you and the companies that were involved in terms of your involvement in structural engineering projects?
Yeah, absolutely. Yeah. This was the first thing that we defined. So design 0 was the prescriptive one. We wanted to see what would be the behavior if we you know, just have the designed building, and of course, we have an indeterminate performance if we don't do any engineering to that. So that was design 0, so prescriptive. Design 1 was we can modify the insulation so that we can allow for the occupants to evacuate to a public way or to a refuge area. So essentially, we are protecting the means of egress only to withstand without collapsing, but only for that means of egress. So this is engineered, so this is PBD, this is performance-based design. We can, but it's only focuses on the means of egress, but that's not applicable for a high-rise building because evacuation to, for example, to a public way on the streets may take hours. So, you know, the fire rating will may be less than that. Also, it may have collapse of the building. So more appropriately for a high-rise building, we want to have no collapse anywhere in the building for a full fire burnout, and that's design 2. So also design 2, we can modify the insulation, but we cannot modify the structural system. So we can only say increase or decrease the fireproofing wherever we want, but the design of the structure is exactly the same as it would be without fire. But for the design 3, which is the best that we want to do in a performance-based design case, we are able to modify both the insulation and the structure. In our case, we modified the connections, for example.
Yes.
But it could be something else. It could be upsizing of columns, of beams, changing sizes, anything.
Thank you. Yes, and that distinction was important. You mentioned for you identified some adjustments needed in the connections. Some other projects, some of the other teams, they had to increase the amount of reinforcement in the slab. Thank you. There is another question about the truss model. Could you please explain how you divide the whole building and how you decided which section of the buildings to study? With the upper floors, and where you cut, what boundary conditions you use.
Right, yeah. So we decided to model, so first of all, we decided that we want to focus on the trusses, right? And because it's a unique structural feature of the building. Now, we wanted to see what is the effect of the trusses behavior on the building. That's why we modeled the rest of the building above the trusses, because they are supported by them. We didn't consider what happens below the trusses in this analysis because they wouldn't be affected by a fire, right? And because this was a larger model, because we wanted to see what the deflection of the upper floors would be, we chose SAFIR and beam elements because it's meant for this reason. It's easier to do that in SAFIR than, let's say, Abacus or other software. So the boundary conditions, we have fixity at the bottom of the columns, which are here. I don't know if you can see my cursor, at the bottom of the building of the transfer trusses. And then also at the concrete core nodes, we also applied fixity. We didn't model the concrete cores. We assumed that they were rigid. But that's why we selected the upper portion. So in that case, we were heating up only the transfer trusses, but only in that red box, which was the room on fire. But then we were taking results everywhere in the building, all the beams above in terms of deflection. And we wanted to do that so that we know what's the consequence of a fire, right? If we see too much deflection, then that's a large consequence, because even if you don't have collapse, you have major damage in non-structural elements, let's say the floors, the doors, the windows, everything is, crooked and deflected. And we wanted to see the effect of insulation. Let's say adding more insulation will decrease the deflection of the upper portion of the building, so the damage will be less. But that's a trade-off in cost for upfront in insulation. So more insulation and less deflection, which was more upfront cost. Or you may want to say, let's apply less insulation now, but then in case of a fire, I'll have larger deflection later, which means much more cost in repairs if they are able to repair the building. So that's why we had different options of how much insulation you put and what's the consequences of that.
Thank you. Very good. We have another question. Broadly speaking, if you could comment, maybe as part of TT and the forensics team, question is, what is the percentage of new building designs that consider the performance-based structural fire design? Well, maybe not, you don't have a percentage, but in general, like how frequently do you see that? And maybe I would extend, since you are part of the forensics team, if you can include forensics types of analysis, maybe. So basically, when in your practice are you applying these type of tools?
Yeah, absolutely. So we have done a design of multiple projects. It is fairly rare. It's not like your everyday project for sure. It's not your everyday residential design or your typical office design. It is for more, let's say, unique structures. So we have done it for more iconic structures, for example, the shed at Hudson Yards, or some renovation project that we did in Boston, or we've done it for Pittsburgh International Airport, which is an iconic, unique structure. So we have several design, or for industrial applications, where there's a benefit of, let's say, reducing fireproofing. So we have done several projects, but it's not like, I don't know the percentage, but it's not your everyday for sure design. It's not done for all the projects for sure. What was the second part of the question?
that happens also in forensics because you're
I'm sorry, yeah. The forensic investigations. Yeah, absolutely. We've done forensic investigations on the impact of the fire in a structure. We also do the fire dynamics side, so the FDS side of it. So how a fire would develop and what would be the effect on tenability, for example, with whether people could evacuate or whether people would be able to survive a fire. And for the structural side, we would, in addition to running structural analysis, would also pair this kind of projects with material testing. So we have capability for material testing, concrete and steel, and in order to define the extent of damage after post-fire, and then defining the extent of damage, and in addition to that, designing repairs, demolishing a part of the structure, shoring it so that it's safe in the short term, and in the long term, designing a repair scheme if possible, or demolishing the structure. So all these phases we have been involved with.
Excellent. Thank you very much for the answer, Jenny. We have a last question which deals with the load combinations that were used in this model that we see on the screen. So when you were interested in the deformations in the upper residential floors, what loads were applied on the model?
We applied the gravity loads per the ASC extreme event, which is the gravity loads plus fire, which is temperature increase or reduction in capacity, and also the thermal expansion.
Okay, so the question was about whether that's combined with wind, for example.
No, I'm sorry. I can tell you the combination is 1.2 dead load and 50% live load. And there's no wind, no, because the extreme event is fire, and statistically we don't combine extreme events. So we assume, for the sake of simplicity and statistically, that a fire would not happen at the same time as a major earthquake or a major wind event.
Great, thank you. Well, thank you very much again, Jenny, for this great presentation and the discussions.
Thank you for having me. Really appreciate it.